Smog is a type of air pollution formed by a mixture of smoke, harmful gases, and fine particles, reducing air quality and visibility. It is mainly of two types: classical sulfurous smog and photochemical oxidizing smog. Smog is caused by vehicular emission, industrial pollution, stubble burning, and construction dust, often worsened by winter weather conditions. Its composition includes PM2.5, PM10, SO2, NOx, CO, ozone, and VOCs, leading to serious health, environmental, and economic impacts, which the government addresses through NCAP, GRAP, BS6 norms, and public awareness initiatives. What is smog? Smog is a type of air pollution formed by the combination of smoke, fog, and harmful chemical pollutants present in the atmosphere. The term smog is derived from the words smoke and fog, indicating its composite nature. It develops when pollutants released from vehicles, industries, and burning activities react with atmospheric components under specific weather conditions. How smog is formed? Smog is formed when pollutants released from vehicles, industries, and burning activities accumulate in the atmosphere and undergo chemical reactions under specific weather conditions. Factors like sunlight, high moisture, and temperature inversion prevent dispersion of pollutants and intensify smog formation. Emission of primary pollutants such as PM, sulfur dioxide, nitrous oxide, carbon monoxide, and VOCs from human activities. Chemical reactions between NOx and VOCs in the presence of sunlight form secondary pollutants like ozone and PAN. Unfavorable meteorological conditions. Low wind speeds, high humidity, temperature inversion trap pollutants near the ground, creating dense smog. Types of smog. Smog can broadly be classified into two major types based on its composition and formation mechanism. Classical smog, London smog, or sulfurous smog. Formation conditions. Develop in cold, humid winter conditions, often during temperature inversion, which traps pollutants close to the ground. Primary source. Caused mainly by burning of coal and heavy fossil fuels in industries and for domestic heating. Major pollutants dominated by sulfur dioxide, smoke, soot, and sulfuric acid aerosols formed due to high moisture. Chemical nature, known as reducing smog because it contains reducing agents rather than oxidant. Appearance and effect. Appears as a dense grey-black haze, drastically reducing visibility and creating choking conditions. Impacts. Causes severe respiratory illness, corrosion of buildings, and historically led to high mortality. Example: Great Smog of London 1952. Photochemical smog. Los Angeles smog or oxidizing smog. Formation conditions. Forms in warm, dry, and sunny climates where strong sunlight triggers chemical reactions in the atmosphere. Primary sources. Originates mainly from vehicular emission, especially nitrogen oxides and volatile organic compounds (VOCs). Major pollutants. Contains ground level ozone, peroxyacetyl nitrate, PAN, aldehydes, and other secondary oxidants. Chemical nature, known as oxidizing smog due to the dominance of strong oxidizing agents like ozone. Appearance and timing. Appears as a yellowish brown haze with peak intensity during afternoon hours. Impacts. Causes eye and throat irritation, aggravates asthma, and reduces lung function and damages crops, rubber, and painted surfaces. Causes of smog. Smog is caused by a combination of human activities and unfavorable meteorological conditions that lead to the accumulation and chemical transformation of air pollutants near the Earth's surface. Vehicular emission. Exhaust from cars, buses, and trucks releases nitrogen oxides, carbon monoxide, and hydrocarbons, which are primary contributors to photochemical smog in urban areas. Industrial activities. Thermal power plants, refineries, brick kilns, and manufacturing units emit sulfur dioxide, particulate matter, and toxic gases that intensify smog formation. Burning of fossil fuels. Extensive use of coal and petroleum for electricity generation, heating, and cooking releases smoke, soot, and sulfur compounds into the atmosphere. Agricultural stubble burning. Seasonal burning of crop residue, especially in northern India, adds large quantities of particulate matter and gases, worsening smog episodes. construction and road dust. Large-scale urban construction, mining, and poorly maintained roads contribute fine dust particles PM10 and PM2.5 that remain suspended in the air. Open waste burning. Burning of municipal solid waste and landfill fires release toxic fumes, dioxins, and particulate matter, aggravating air pollution. Meteorological conditions, temperature inversion, low wind speed, high humidity, and calm atmospheric conditions prevent dispersion of pollutants. Urbanization and population growth. Rapid growth of cities increases energy demand, vehicle density, and industrial output, all of which elevate smog levels. Composition and pollutants involved in smog. Smog is a complex mixture of primary pollutants released directly into the atmosphere and secondary pollutants formed through chemical reactions under specific climatic conditions. Particulate matter PM2.5 and PM10. Fine particles originating from vehicle exhaust, coal burning, construction dust, and biomass burning. PM2.5 penetrate deep into the lungs and bloodstream, making it highly harmful. Sulfur dioxide, emitted mainly from coal-based power plants and industry, reacts with moisture in the air to form sulfuric acid aerosols, a key component of classical smog. Nitrogen oxides, released from vehicle engines and industrial combustion, act as precursor pollutants in the formation of photochemical smog. Carbon monoxide, produced by incomplete combustion of fuels, reduces oxygen carrying capacity of blood and worsens respiratory stress during smog episodes. Ground level ozone, a secondary pollutant formed by the reaction of nitrogen oxide and volatile organic compounds in the presence of sunlight, a major irritant in photochemical smog. Volatile organic compounds VOC, emitted from fuels, solvent, paints, and industrial processes, play a crucial role in ozone and pan formation. Peroxyacetyl nitrate (PAN), a toxic secondary pollutant responsible for eye irritation and damage for vegetation. Smoke and soot, carbon-rich particles released from fossil fuel and biomass burning, contributing to reduced visibility and health hazards. Trace heavy metals, elements like lead, mercury, and arsenic present in industrial emissions, adding to the toxicity of smog. Smog impact. Smog has wide-ranging impacts on human health, environment, economy, and daily life. Prolonged exposure to smog significantly lowers quality of life and poses a major challenge to sustainable urban development. Health impacts. Causes respiratory problems such as asthma, bronchitis, chronic obstructive pulmonary disease, and lung infections. Increased risk of cardiovascular diseases including heart attacks and strokes. Leads to eye irritation, headaches, fatigue, and throat discomfort. Affect children, elderly, and pregnant women more severely due to weaker immunity. Long-term exposure can result in reduced lung capacity and premature deaths. Environmental impacts. Reduced visibility, disrupting road, rail, and air transport, damages crops and vegetation, especially due to ground-level ozone affecting photosynthesis. Leads to acid rain formation, harming soil, water bodies, and forest. Alters local climate conditions by trapping heat near the surface. Economic impacts. Increases healthcare expenditure due to rising pollution-related illness, causes loss of productivity from sick days and reduced work efficiency, result in school closure, work restriction, and emergency measures during severe smog episodes. Negatively impacts tourism, aviation, and outdoor economic activities. Social and urban impacts. Reduce overall quality of life in cities, forces vulnerable population to remain indoors, affecting mental well-being, highlights environmental inequality as poorer communities are more exposed to polluted environments. Smog monitoring and measurement. Monitoring and measurement of smog are essential for assessing air quality, issuing health advisories, and implementing timely control measures. In India, smog is monitored through a combination of ground-based station forecasting systems and satellite observation. Air Quality Index (AQI) is a standardized numerical scale used to communicate air pollution levels and associated health risks. It integrates concentration of major pollutants like PM2.5, PM10, NO2, SO2, CO, and ozone, lead, and NS3 into a single value. Government initiatives and policy measures. National Clean Air Program (NCAP) aims to reduce particulate matter PM2.5 and PM10 concentration by a targeted percentage through city-specific action plans. Graded Response Action Plan (GRAP) implements emergency measures in Delhi NCR during severe smog episodes such as restricting vehicles, banning construction and closing schools. Bharat State 6 BS6 emission norms introduced stringent vehicular emission standards to reduce nitrogen oxide, sulfur dioxide and particulate emissions from vehicles. Commission for Air Quality Management ensure coordinated and integrated management of air pollution across Delhi NCR and adjoining states. Promotion of electric vehicles. FAME scheme and state EV policies encourage cleaner transportation to reduce vehicular pollution. National Electric Mobility Mission supports transition to electric and hybrid vehicles to curb emissions. Control of industrial emissions mandates installation of pollution control devices and adoption of cleaner fuels in industry and power plants. Stubble burning management measure provides incentives, machinery and alternative to farmer to discourage crop residue burning. Expansion of public transport. Investment in metro rail, buses and non-motorized transport to reduce private vehicle dependence. Challenges in smog management. Interstate nature of air pollution. Smog often results from pollutants transported across state boundaries, making coordinated action and accountability difficult. Weak enforcement of pollution norms. Poor monitoring, limited manpower and regulatory gaps reduce the effectiveness of existing environmental laws. Rapid urbanization and vehicle growth. Increasing population, urban sprawl and rising vehicle ownership continuously add to emission levels. Economic dependence on polluting activities. Industries, construction sector and farmers rely on practices that contribute to smog limiting strict action. Seasonal agricultural practices. Crop residue burning remains prevalent due to time constraint and lack of affordable alternatives for farmers. Inadequate public awareness. Limited understanding of pollution sources and health impacts hinders behavioral change at the individual level. Way forward. Strengthen regional and interstate coordination. Studies show that 30 to 40% of Delhi NCR winter smog originates from outside the city, highlighting the need for coordinated action among Punjab, Haryana, UP, Rajasthan and Delhi through bodies like CAQM. Accelerate clean energy transition. India still derives over 70% of its electricity from coal, a major source of sulfur dioxide and particulate matter emissions. Rapid expansion of renewable. India's target 500 gigawatt non-fossil capacity by 2030 can significantly reduce smog-forming pollutants. Improve urban transport systems. Vehicular emissions contribute nearly 40% of PM2.5 pollution in major cities. Expanding metro networks, electric buses and EV adoption target of 30% EV penetration by 2030 can substantially cut nitrogen oxide and VOC emissions. Address agricultural stubble burning. Satellite data indicate that stubble burning accounts for 20 to 35% of peak PM2.5 layers in North India during October-November. Scaling alternatives like happy seeders, biodecomposers and biomass-based power plants is critical. Strengthen industrial emission controls. Thermal power plants contribute around 50% of SO2 emission in India. Enforcing flue gas desulfurization units and cleaner fuels can reduce classical smog components. Enhance air quality monitoring and forecasting. Currently, India has air quality monitoring stations in only 800 locations, which is insufficient for a country of its size. Expanding real-time monitoring and early warning systems like SUFFER can enable timely preventative measures.